Okay, so let's continue our lecture on Locus. So I will review a little bit for you. So what is Locus and what is used for? Locus is a method to design a controller, uh, specifically the way to find the gain for a controller. So in our system, we have a transfer function shown in here. This is a specific case. And we want to control using negative feedback. So here is the reference and this is the actual response. So in order to have the output approach to the reference, we need to choose appropriate gain k. So by increasing the gain k, we can see the different the evolution of the pole for the closed loop. So here this one is transfer function of open loop, but once we make a negative feedback, we have a closed loop transfer function, and the closed loop transfer function has denominators like this. Okay, so when we increase value k, then we have different roots of the denominator, which is called poles. Okay, so in this case, just an example that the denominator is second order polynomial, so the roots of the denominator are p1 and p2, and they are poles for the closed loop transfer function. So if we increase value k here, we can see that the imaginary number increase. Okay, the coefficient of imaginary number increase, which cause the response in time to oscillate. Okay, because a characteristic equation that has complex number induce the solution of in the time domain in the form of trigonometric function. That's why there is oscillation. So we get the idea that, well, if we choose appropriate value of k, then we might have the response that we desire. Maybe slight overshoot, slice oscillation that we like. So actually, there is a way to draw the curve of the poles of the closed loop transfer function when we try to increase the value of k. And so this is an illustrative example for the second order system that you just saw earlier. Um, so when the k equal to 0, actually the poles of the closed loop transfer function is the same as pole of open loop transfer function. So the pole of open loop is 0, the R0 and minus 2. And when we increase the value of k, the pole of closed loop start to shift, okay, shift until they become double roots before they depart or break away to become complex number. Okay, and so this lecture is to give you some rule, sketching rule, so that you can sketch rule locus. So given the poles and zeros of open loop transfer function, then you can apply the rules to draw to sketch the rule locus. Uh, so yeah, the rule is derived from the characteristic equation of the closed loop transfer function. So this is just a remind to recall what the characteristic equation looks like for closed loop transfer function. Okay, so in this case, for non-unity negative feedback, it means the feedback has also transfer function. So the most important thing is the characteristic equation. If we have non-unity negative feedback, h of s, then h of s appear here next to g of s. So this is very easy to remember, to notify. Um, if this one is just unity, then you have h of s just one. So you got only one plus k g of s, something like that. So I'm not going to explain in detail again. I will uh, okay, recall a little bit the terminology of Locus. For example, real axis segment, which means the curve that is located on the real axis, okay, and must be located in particular place, not all over the place. Okay? And then you got breakaway points. Breakaway point is this one. So when the roots become the ball and then try to break away to become complex number, so this point is called breakaway. And asymptote, asymptote can be drawn, and the root locus must approach to asymptote when k approach to infinity. Okay, so this curve just go approach to asymptote like this. This one also have one asymptote this way, and so asymptote can be defined by asymptote real axis intercept and asymptote angle. Okay. We just need to find these two parameters, okay, intercept on the real axis and angle, then we can draw asymptote easily. Another one is break in. So we have break away point from the the ball root on the real axis, and then we have break in. Okay, and also intersects with the imaginary axis here. It's called imaginary axis intercept. So the intercept on the real axis always break in or break away point, but at the imaginary axis, the intercept is always symmetry. Okay. Then we have some rules in order to draw the rule occurs. Rule number one is just to give information for validation. So if somebody have drawn rule occurs and you look at the rule number one to verify whether it's violate or not, it's violate, then 100% is wrong. So the rule number one is number of branches must equal to numbers of poles. Rule number two, always symmetrical about the real axis, because the root from polynomial of the denominator of the closed loop transfer function always have all pure real number or complex conjugate. So complex conjugate means if you have plus omega j, you also have minus omega j. That's why uh, the curve rule occurs always symmetric with respect to real axis. And rule number three, that is very, very important that you can start to draw the rule occurs. And it's said that real axis segments are to the left of the odd numbers of the real axis finite poles zero. So if you have poles of zero on the real axis and then you label number by 1, 2, 3, 4, 5 from right to the left in this way, 1, 2, 3, 4, something like that. Okay? So real axis segments must be located on the left of odd number, on the left of number one, on the left of number three. Okay, if you have number five, real axis segment can locate on the left of number five too. Okay? Um, then rule number four, rule occurs always begin at poles. Pole here means pole of open loop. Okay? transfer function and ends at zeros of the open loop transfer function. Okay, state here. And so here I have already demonstrated, explained in the mathematical term why we can state this rule. Okay, and then this one. Okay, pole and zero at infinity. So for proper system, we only have degree of denominator greater or equal to the degree of numerator. Okay. So when s approach to infinity, there can be zero, right? Because the degree of s on denominator is higher, right? So for example, if we have a third order system like this, and if we take a limit of s approach to infinity, okay, for like s means uh, s going to infinity, then we can reduce it to be just k over s to the 3. That means there are three zeros at infinity. It means s somewhere at infinity, 3s somewhere at infinity, that make the transfer function 0. 10, uh, 10 to 0, not exactly 0, but 10 to 0. And that's called 0 at infinity. And we just need to know the number, how many number of 0 at infinity. If you have 3, 0 at infinity, it means we have 3 asymptotes. Because asymptote is for guiding the root locus when k approaches to infinity. Okay. So after get to know the finite and infinite zeros, we can, yeah, also finite poles. Then we know the number of asymptotes. Then we can calculate some parameter that can be used to draw asymptotes. Meaning to say the asymptote and real axis segment intercept. Yeah, real axis intercept. Sorry. So this value is scale on the real axis. Okay, when you calculate using this formulation, and you get sigma a, and sigma a is here on the real axis. And for the angle, you calculate following this formulation to find the angle of asymptote number 1, asymptote number 2, and asymptote number 3. Okay, so here, um, so the number of asymptote is the same of the different number between degree of numerator and degree of denominator, right? Degree of denominator equal to the number of poles, right? And degree of numerator is the same as number of zeros. Because if we add polynomial degree 2, we always have two roots. And that two root is finite zero. Right? Same for the numerator. If we have polynomial with 3-degree polynomial, then we have three roots. So let's say if 3 of finite poles minus 2 of finite zeros, then we have just one asymptote. So is that okay? Up to this point, there are so many terminologies in Locus. All right. Do you have questions, Subun? Anyone? You have questions? Hmm? No, but yeah, at least we sometimes we don't need to use software because some simple system like uh, well any uh, Yeah, actually, when you try to design a controller that you do not know, I mean, sometimes you need to put zero and poles by yourself for on a controller. So if you don't have the inside or the shape of the root locus could be, so where you can put zero or pole for the controller. But if somebody give you the controller and just ask you to find the gain, yes, you can use software to find the gain. But for engineer, you sometimes the problem you need to solve that you must choose the particular controller by yourself, right? Um, so let's continue to the next rules, which is rule number 6: real axis break in and break away points. So break in and break away, like here. This means the roots. We have double roots. So and these roots are real number. Then if we take a look the characteristic equation that this plus 1 equal to 0 or this equal to minus 1, then we can easily find k in function of sigma. Okay, and because sigma is double root here, then it means uh, they make the optimal value of k. Okay, so that's why here we can take first derivative and set it to 0 in order to find that particular sigma. So this is a way to find the break in and break away. And here is we sometimes we just need to know approximation. I mean, to design controller we don't need to know very exact, but the most important thing is to know the shape, uh, how you can draw the root locus in particular way. But anyway, all the material here show you how to find all exact number or exact parameter. And this is just example. If you want to find the exact parameter of break away and break in, so just follow this. So this is just a simple mathematics, okay, on rational function, a fractional function. And then rule number 7, very similar to rule number 6, but now for number 6, the intersection is on real axis and the roots are the ball. But here, the intersection on imaginary axis, you got complex conjugate. So it means when you substitute s by j omega, okay, satisfying the characteristic equation, and then um, you can create a, so you can have equation for omega and yeah, the two equation for omega and k. So you need to find value of k that um, make the root on the imaginary axis. Okay, so just follow this process. You can find omega and k. Okay, so let's summarize the rules of root locus sketching. Again, rule number 1, number of branches equal to number of poles. Number 2, symmetrical about the real axis. Number 3, real axis segments are to the left of an odd number of the real axis finite pole zeros. Rule number 4, rule locus begin at poles, ends at zeros. Rule number 5, asymptotes, angles, real axis intercept. Okay, so asymptote can be defined by, can be drawn by real axis intercept and angles, and using these two formulations. Rule number 6, real axis break in and break away point. So this is the process to find the exact break in and break away point. And rule number 7, imaginary axis crossings. Okay. And you can say this is the transition to instability, because if we have roots of the closed loop transfer function on the right half plane, then the system is unstable. Okay, so let's do practice. Number 1, sketch the root locus. Um, so I will show you the first three, and then let you try yourself. Okay. Okay, let's take a look on A. We have two poles. Don't forget that pole from the open loops, also zero also from open loop. Okay, so you can imagine. Let's if I label here is -1, here is -2, and let's say here is 1. Then the transfer function look like this. The open loop transfer function look like this. S -1 goes 0 here, and then S plus 1, S plus 2. Okay, transfer function look like this. Then if we control, we use negative feedback control, then we have closed loop transfer function. And okay, so I mean, so we have this transfer function, let's call g of s. Okay, then we design controller using the gain k, g of s. Just recall what is the purpose. Okay, like this. So when k increase, then these poles, the poles of closed loop transfer function must change according to the number of k, and the value of k, not number, sorry. Well, the best thing to sketch rule locus, you start from the rule number 3, the easiest. Rule number 3 say real axis segment is on the left of odd number, odd number of finite poles and 0. So let's count. This is label. This number 1, number 2, number 3. And real axis segment must be on the left. So here on the left. Okay. So here on the left. Because on the left of this one go to infinity. Then it go to infinity. Okay. And you use rule number 4. Let me see number 4, right? Yeah. Number 3, number 4 is the best rule, I would say. Number 4 say it start from begin from poles and end at 0 or open loop. So this one begin from pole and end at 0. It means this direction. And this one start from poles and at 0. Where is 0? 0 at infinity. That's why we call infinite 0, because s at infinity also make the transfer function 0, right? See, so it means this direction, right? Then look at asymptote. What is the number of asymptote? Number of asymptote is the same as number of infinite 0. So we got one infinite 0, and this one already approached to that 0. It means this is the asymptote already. You can calculate the asymptote intercept, um, and you can calculate the angle. You will got the angle is 180 degree, and this asymptote. So let's apply rule number 5. Here is rule number 5. Number 5, so the formulation of sigma A equal to sum of all the finite poles minus sum of all finite zero over number of finite pole minus number of finite zero. So here finite pole we have minus 1, minus 2, right? And we have 0, just 1. So minus 0, minus 1 like this. And then here is just 1. So we got 4 minus 4. Okay, so intercept is at minus 4. Let's say here sigma A is minus 4. Okay, and we don't know the angle yet, so we cannot draw it, right? I don't know this way or this way or this way. I don't know. So I need the angle with respect to real axis. Then I calculate theta A equal to uh, 2 2k plus 1. Yeah, this maybe use because we have k here. Times pi over yeah, over number of finite poles minus number of finite zero. Okay, which mean 2m plus 1 pi over 1. That is 2m plus 1 times pi. So let's choose m equal to 0. M equal to 0. Then we get theta A equal to pi. If you want to try choose m equal to 1, then you got theta A equal to 3 pi. 3 pi. But it's still the same, right? Pi, 3 pi is still the same. So we got only one asymptote here. Right? Then it's validate all other rules as well.
That's not the second one from the
So yeah, this asymptote, this is angle pi.
and the from the second one
The second,
second part from the second one.
this second part, what do you mean? The real axis segment?
Uh, yes. So, yeah. The second part.
This one?
Not the other one.
Or this one?
Yeah.
So what is your question?
Isn't there an asymptote going from there?
No, we only have one asymptote, right? Only one asymptote because angle always same. So it means only one asymptote. This one because it go to finite zero. This is finite zero, and it already respect the rules. Begin at pole and end at zero. End here. Okay. Okay. So let me copy this. Then let's start. Let's do it for the second example. So this one you can imagine. Oh, um, let's say this is minus 1. Let's say this is minus j, and here is j, right? So the transfer function should look like this. 1 over s plus 1 and then s square plus 1, right? This is open loop transfer function. And well, again, apply the rule number 3 first. The real axis segments on the left of finite pole 0. So how do we count now? We have root here and here. We only count all the poles and 0 on the real axis. So if we start to count, this is 1, only 1. So real axis segment is on the left of the odd number. It means all here, okay, is asymptote. I mean real axis segment to infinity on the left of pole number 1, right? How about, okay, what, and yeah, next rule, what rule should be applied? Well, this one, asymptote, because how many infinite zero? Number of infinite zero. How many do we have? Third order in here and just zero order in here. So we have three, right? We have three. It means we have three asymptotes, right? So we first find sigma A. Sigma A means sum of all finite poles, which is minus 1, and sum of all finite zero, which is nothing, divided by number of finite poles. How many finite poles? Just one. How many finite zero? None. So it means the asymptote is at minus 1, asymptote intercept is at minus 1. Okay. Oh, wait. Why I say one? How many my finite pole? One, two, three. We have three, sorry. Yeah, three. So here is one third, minus one third. So intercept one third is here. Okay. And then angle. For sure that if the difference between finite pole and finite zero is 3, it means we have asymptote 3, then just find the first 3 theta A, right? So theta A is 2m plus 1 pi over 3. Then take m equal to 0, then we have theta A equal to, then m equal to 1, we have theta A equal to pi, equal to 2, then we have theta A equal to 5 pi over 3, which is actually 2 pi minus pi over 3, right? I mean, this one is symmetric with pi over 3, right? Yeah. So let's draw it. The first one is pi over 3, 60 degree. So it means like this. And pi, which means, oh, I should draw it's blue. And another one is this one, okay. And then, yeah, let's draw like this. And this one's symmetric with this, with the first one, okay. So this is pi over 3, this is pi, yeah. And this one actually minus pi over 3, which is like this, minus pi over 3, okay. um then we start to draw the rule locus. So this one approach to this asymptote already. This one approach to this asymptote. Okay, and this one approach to this asymptote, like that. And let's validate with other rules. Rule number one, it say number of branches equal to number of poles. Is that true? Look, how many poles do we have? Three. How many branches we have? Three. All the red, three branches. And symmetrical about the real axis. Is it true? Yeah, this one for sure on the real axis already. So this one, yes, symmetrical with respect to real axis. So validate. Yeah, it's validated. Begin at poles and end at zero. So begin at pole and at zero. So I mean we have this direction and this one end at zero, but zero is infinity, so it go to the direction. Go direction. So it validate rule number four. And rule number five, we just got it from this rule. And breakaway points we need to find. Uh, yeah, actually in this case there's no breakaway point. And real axis intercept, yeah, we can find, but we don't have to for now. Okay. Okay. Then this one. How many poles? How many zero? Two finite poles, two finite zero. Which means, so how many infinite zero? Samnan, can you answer how many number of infinite zeros? Infinite zero. Okay, so transfer function should look like this. So we have s, let's say this one minus 1 minus 2, s plus 1, s plus 2 for the numerator, and for denominator let's say this one j and this one minus j. So here is s squared plus 1, right? So we have the same degree of numerator and denominator, same order. And if we take limit as approach to infinity, we don't get zero, right? When s approach to infinity, then we have, yeah, 1. We have g of infinity is 1. It means it cannot be 0. So I mean it does not have infinite 0. So it does not have asymptote. See? It does not have asymptote. And let's check with other rules. But first start rule number 3, real axis segment on the left of finite pole 0, finite 0. Let's count first, or let's label first. Number 1, number 2. Real axis segments must be on the left of odd number. So here, just here. So no other real axis segment. And then let's think about, uh, because we have two poles, we have two zero. And rule number 4 says that begin at poles and end at 0. So this pole must end at 1 0, and this pole must end at another 0. Okay. So let's say if I say, oh, okay, so I think this one may go to this one, and this wing maybe go to this one. Just try this way and check with other rule whether it validate or not, it violate or not. Let's see number 1, number of branches equal to number of poles. Is it fine? Is it fine? I don't think so. This one already violate.
No, it's asymmetric.
Yeah, that one also not violate. But let's see now rule number 1. 1 branch, 2 branch. How about this? Three branch. So more than number of poles, right? Mm. And rule number two, symmetrical about real axis. So totally wrong. This is totally wrong. Not symmetric at all. So how can you have symmetric? Well, it must intersect somewhere, right? Like this. So it must have the ball root here. So it means one brand this go this way. I should draw a different color. So one brand go like this, and like the 2 this 0, for example. And another branch go from here, intersect here, and then go to this one. So number of brand equal to number of poles. Validate. Okay, rule number one is validate. And number two, symmetrical about reaxis. Yes. Number three already. Number four, begin at pole and at zero. Yeah, we draw it following that rule already. So this is rule occurs for this transfer function. Okay. So try to think by yourself for number or for D, for example D. Is there any relaxation segment? No. There's no odd number of pole zero here, right? No relaxation segment. How many infinite zero? Infinite zero. How many? Infinite. Yes, two. Two infinite zeros. So it means there are how many asymptotes? Two asymptotes. Yes. And don't forget, symmetric about real axis segment. So I mean, if you only have two asymptotes, which means this two asymptotes must also symmetric with respect to real axis segment. Real axis. So you just draw asymptote, and then you can draw the rule locus for this case. So two asymptote. So you can immediately go to this formulation 2m plus 1 pi over 2. So m equal to 0, then theta a equal to pi over 2. And m equal to 1, then theta a equal to uh, 3 pi over 2. Or yeah, we can also use this way. So your asymptote is, yeah, so asymptote is like this and like this. And so what about the rule of gas? Yeah, it's just like this. Go to zero like this. Zero in infinity like this, and then like this. That's it. How about this one? And real axis segment. You can have real axis segment. Label is number one, number two, number three, number four. So real axis segment on the left of the real odd number, like this. Okay, and we have four asymptotes, right? Because infinite zero, we have four infinite zero. Or the easiest way maybe to think number of finite poles minus number of finite zero. You don't have finite zero, and you have four finite poles. So you have four asymptotes, right? Four minus zero is four, so four asymptotes. And for asymptotes, you straight go straight to this one. theta A equal to 2m plus 1 pi over 4. Okay, and just start from equal to 0, then you get theta A is pi over 4. Equal to 1, then you have theta A equal to um, 3 pi over 4, right? 3 pi over 4. So let's say you can draw, okay, you need to find sigma first. Let's say it's minus 1, minus 2, minus 3, minus 4. Sigma A is minus 4, minus 3, minus 2, minus 1, minus, there is no finite 0 over 4 like this. So you have 3, 6, 10, 10 over 4, it means 5 over 2. So 2.5 is here, right? Minus, minus 2.5 is here. We put the black one. And yeah, I just need these two. I don't need to find all of them because they are just symmetry with respect to real axis. So this is pi of 4 and then 3 pi of 4. Oops. And then this one just symmetry and this one is just symmetry. Okay. So asymptote. Okay. So root locus like this. It begin from root or from poles and then it end at 0. Okay. Like this. Okay. So I'll try to finish the last one before we have a break. Okay, this one start from real axis segment. Level 1, 2, 3, 4. Then real axis segment. Real axis segment. Number of asymptotes, 2 poles minus number of 2 zero, it means 0. 2 minus 2, 0. No asymptote. So remember that it begins from poles and end at 0, which means this pole will end at this 0. This pole will end at this 0. Right? So how to go there? To have symmetric, don't forget, and only two branch. Oh, yes, two branch. But you only have two pole. You have only two branch. So how can you draw two branch? So let me use the green. So this one go here and add this one become double root. Go this way. And then it go to this 0, for example. And another one, this one from here, and most symmetry like this. Okay.
And we choose the shape of the parabola or
The shape is supposed to be ellipse. Only
like
part, only special case, ellipse can be circle.
and the size we don't care about how far we go.
Yeah, so it depends on. We need to know exact pole, exact 0. Then we can. Yeah, but actually the most important thing is that, well, if we can have the pole around here, we got stable system. So it means somehow k is large. K is large, we have stable system. If k is too small here, it's not stable, right? So we can try without increasing k, because k go to infinity, we will get roots around this 0 on the left hand side. Okay. This one is like this. Okay. Let's take a break for 15 minutes.